Name three methods that can be used to solve a system of linear equations. Whenever you have the two equations with x and y, that's a system of linear equations. We talked about graphing the solution where they intersect. Elimination is the method that we use in all the cases. And then substitution, where you would solve for a variable, so like you'd get y equals or whatever, and then you'd plug in what that is into the other equation. But you can always use elimination. So substitution is kind of a luxury to know how to do it, if you want. 8b, fill in the blank. When graphing a system of linear equations, lines that intersect at one point have one solution. They only intersect at one spot, that's the solution. Lines that intersect at every point have infinitely, so first blank is 1, second blank, lines that intersect at every point have infinitely many solutions. And for that to work, is you could think of like if I were to draw one line and then I were to draw the other equation is the same. So they literally lay perfectly on top of each other. So that would be infinitely many solutions. They call it coinciding lines. And then lines that do not intersect have 0 solutions. So that's just basically parallel lines. They have the same slope. They'll never intersect. There is no solution. So moving forward. All right, for number 9, we have to graph inequalities, which really we're going to graph it the same way we would an equation, and we're going to use slope-intercept form. So when anything is solved for y, we can say that's slope-intercept form. So like y equals mx plus b, m is your slope, b is your y-intercept, or where the line crosses the y-axis. So in this case, my slope is 1/2, and my y-intercept is -5. So let me go ahead and graph that. And if it's greater than, this is a dashed line. And if it's less than, you would use a dashed line. If there is a solid line underneath the inequality sign, so it's greater than or equal to or less than or equal to, you use a solid line when graphing. And since it says y is greater than, if you think of greater than, you usually would think of above. So you're going to shade above in this case. If this was a less than sign, you would shade below the line. So in this case, make my graph over here. So I'm going to go down to the -5 y-intercept, so right on the y-axis. And it's rise over run, 1 over 2. So up 1 over 2, up 1 over 2. So it looks like this. And again, it's a dashed line because it cannot equal y. And it's going to be, we're going to shade above it because it's greater than y. So everything above that is a solution to the 1 equation, or the 1 inequality. Now the other inequality is y minus 4x less than or equal to -1. This is not in slope-intercept form. So we'll just solve for y to put it into slope-intercept form. So I'll add 4x to both sides. So I get 4x minus 1. Now my slope is 4, which is like 4 over 1. So I'm going to rise 4 and go over 1. My y-intercept is -1. So I'm going to go down to -1, plot the point, and start there. Then I'm going to go up 4 over 1. I'm going to apply the slope. So up 4 over 1, up 4 over 1. I'm going to put a solid line in because it can equal it, and I'm going to shade below because it's less than. So solid line. I'm going to go back down here. Shade everything below, and yeah. So all this green shaded area, anything that's in this region here is a solution to the inequality. You could pick any point in here, plug it back in to either inequality, and it would end up being true. Just make sure it's recording. Yep. All right, so tan I have y is greater than or equal to 2x, which you can think of as 2x plus 0. So here, my slope is 2 over 1, and my y-intercept here is just 0. And I have my other inequality, which is y is minus 2x. Y minus 2x is less than 6, not in y-intercept form, so we'll add 2x to both sides. So I get 2x plus 6. And then here's my slope, 2 over 1, and which is going to match up with the other slope, so those are parallel lines. And then I'm going to graph this. So I'll graph the first inequality. My y-intercept is 0, so it's right there at the origin. And then I'm going to do a slope of up 2 over 1, up 2 over 1, up 2 over 1. I'll go down 2, back 1, down 2, back 1. And it's a solid line because it can equal y. It's going to shade above because it's greater than. That's the one inequality. Now let's graph my second inequality there, where my y-intercept is positive 6. So up 2, 4, 6. And then a slope of up 2 over 1, or down 2, back 1, down 2, back 1. And that is not a solid line because it cannot equal y, so it's a dashed line. And then it's less than, so we're going to shade below. So it's going to go right there. In fact, you don't even have to have all this yellow stuff out here because it's not going to be a solution to both inequalities. And so it would be like this little strip in between these two line inequalities. So that's graph inequalities. Now let's move to exponents. So 11a, it says evaluate 2 to the negative 6th power. So a negative exponent, if something is in the numerator, it's going to go to the denominator. If it's in the denominator, it goes to the numerator. So you can even think of this as a 2 to the negative 6 all over 1. And what we're going to do here is the exponent, negative 6, this will move this 2 down to the denominator with a positive 6 exponent. So this is going to be 2 to the 6th in the denominator. And don't just leave it a blank numerator. There's actually still a 1 up there, okay? So it's 1 over 2 to the 6th, which 2 to the 6th power is 64. So, and then it says evaluate 3/5 to the negative 2. Now, you can use the negative exponent property right now, or you could go ahead and square it first, but let's do the negative exponent right now, which you can just flip this fraction right now, write it as 5/3, or if you want to use the power rule, you can think this is 3 to the negative 2 over 5 to the negative 2, because these are both being raised to that exponent. So now, if it's a negative exponent, here again, 3 in the numerator is going to go to the denominator with a positive exponent. So positive 2 squared. This denominator here, 5 to the negative 2, I'm going to move it to the numerator with a positive exponent. So it's 5 squared over 3 squared, which is just 25 ninths. 12a. So I have x to the negative 3rd, y to the 4th, z to the 0. So I'm going to simplify this. So I'm going to make like just my fraction line right now because I think it's easier to do that ahead of time. X to the negative 3rd. This is all in the numerator. This is all above. So I'm going to do x to the positive 3rd here in the denominator. All right, so now we did that one. Y to the 4th. That's going to stay in the numerator because it's a positive exponent. Z to the 0th power. Anything raised to the 0th power is just 1. So it'd be like y to the 4th times 1 over x to the 3rd, which is just, of course, y to the 4th over x to the 3rd. So, that is 12a. Oh, we got 12b here. So I have a to the 6th, y to the 8th squared. So this is a power of a power rule. If you want to think about it, this is really like a to the 6th times y to the 8th times a to the 6th times y to the 8th. Because it's squared, it's multiplied to itself. So when I go ahead and simplify this, I have 6 a's being multiplied here. I have another 6 a's being multiplied here. So I have a total of 12 a's being multiplied. So you can just add your exponents when you're multiplying. All right, you have the same base. All right, you can add your exponents. So 6 plus 6 is 12. Here I'm going to do 8 plus 8 and get 16. But again, conceptually, you can think of it, this is 8 y's being multiplied, like y times 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 y. All right, and then here's another 8 y's being multiplied for a total of 16 y's being multiplied. So there, that is done. 13. So I have 2 to the x negative 3, y to the negative 2, all over 6z to the 4th. So we got to simplify this. I'm going to put my fraction sign there, or division sign. 2 to the 6th, that's going to reduce 2 over 6. So that just becomes a 3. We reduce that fraction because 2 goes into 2 once, 2 goes into 6 3 times. All right, so I got a 3 down here. Then I'll do x to the negative 3rd. That's in the numerator with a negative exponent. I'm going to write it in the denominator with a positive exponent. Then I'll do y to the negative 2. So that's going to move to the denominator as well with a positive exponent. And then z to the 4th, that's a positive exponent. It's going to stay where it is. So this is z to the 4th. And again, you can't have a denominator with nothing in the numerator. So you have your 1 up there. So it's 1 over all that. $14. There's a few techniques you can use, really, that'll all be right. In this case, let's just simplify this fraction first. So I'll just show you kind of what's going on here. If I have 4p to the 3rd, that's like p times p times p, all over, and then 2p, and then q to the 4th. I got 4 q's being multiplied. And that's all raised to the 4th power. I'm going to just simplify this fraction first because I can see some stuff that's going to divide out. So the 4 and the 2, this is going to become a 2 in the numerator. I'm going to have a p and another p divide out. So I'm left with 2 p's. And you can think about it here. I got p to the 3rd. I got 3 being multiplied. I have to take 1 away because it's going to divide out. So I have 2p squared now all over q to the 4th. And that's all raised to the 4th power. So, you could expand this out even if you want, where you'd have 2p squared all over q to the 4th, multiply that to itself 4 times, and work with that. Or the short way here would be to use the power of a power rule. So we're going to go ahead and multiply our exponents together to this 4th power. So here I have 2. You can even think of it as a 2 to the 1. So here I have 1 times 4, which is 2 to the 4th. I have p squared. I'm going to do 2 times 4. So I'm going to do p to the 8th. Notice I'm not adding them. This is a power of a power rule. I'm raising it all to this other exponent. So I'm going to multiply my exponents all over q. And then I have a 4 times this 4 is q to the 16th. And then I'll just double check, make sure nothing's going to divide out. No, they all have different bases, but I can write 2 to the 4th as a 16. So that's 14. All right, now we're going to branch into polynomials. Time here. Yeah. So 15 here. For the polynomial, I have 5x 4th y squared minus y to the 5th z squared. So what's the degree of the polynomial? The degree of the polynomial is, you got to look at, I have 2 terms here, and whichever one has the exponents that add up to the most. So here I have 4 and 2. I have a total of 6 exponents here. I have 4 x's being multiplied and 2 y's being multiplied. So this has a degree of 6. This has a degree of 7. So you just take your highest degree. So what is the degree? It's 7. For the polynomial